Good afternoon, everybody. Good day before spring starts, end of winter afternoon. Welcome to today's Liftoff webinar brought to you by LIFT, the National Advanced Materials and Manufacturing Innovation Institute, where we drive American manufacturing into the future through technology and talent development. LIFT is a public-private partnership where we convene and connect government, industry, and academia in the fields of advanced materials, manufacturing processes, systems engineering to enhance manufacturing competitiveness, national economy, and our national security. Welcome again. My name is Christine Longroy, Senior Director of Industrial Base Engagement for LIFT, and it is my honor to introduce our presenter, Adam Hope, who is Customer Relations Manager for Thermo-Calc Software. He is a PhD in welding engineering, and his work is focused on integrating computational and experimental techniques to predict susceptibility, not so easy for me to say, to different types of weld cracking. So Adam, welcome. Look forward to your presentation. And folks, I'd like to remind you, for those of you that have questions, please make sure that you put those in the chat, and we'll get to those after Adam's very comprehensive presentation today. So thanks for joining us, and Adam, take it away.
Great, thanks, Christine. Yeah, so today, as Christine said, I'm going to talk about the additive manufacturing modeling that we can do now inside of Thermo-Calc. And to start it off, I'm going to talk a little bit about the influence of both temperature and chemistry on material properties, microstructure, and also some properties like thermophysical properties. And so it's kind of maybe a busy slide, but starting here off on the right, let's just look at this figure over here. We've got a finite element model, and this all comes from a nice paper by Smith and others. We've got a finite element model that's to predict the temperature in a additive build. So we're looking at a specific node in that simulation, and the laser's coming across. And as the laser crosses the node we're looking at, the temperature goes up. We get some melting and maybe some superheating, and then we cool back down. And we have solidification over here. You can see by the knee in the cooling curve, and this all happens relatively quickly, right? And if you want to make such a model, such a finite element model, you need to have material data. This happens to be for 316L stainless steel, as was done in the paper here. But where are you going to get that data? You need to have the specific heat, the latent heat. You might need to have we should have the thermal conductivity, things like density if you're going to try to predict residual stress or elastic modulus. And all of those properties are going to be integral to how the model works. And you can look those properties up in a handbook, which might be what you do, or maybe even the finite element software you're using has some values inside of it for some kind of alloy, maybe it's 316 or 304. And that's one way. And a lot of times those values may not be temperature dependent. So if you go and look in the handbook for a specific heat up here on the top left figure, you might just find it's a fixed value, 0.5. That might be the room temperature value, and it may not vary as a function of temperature. Same with latent heat. You might find a single value with a liquidus and a solidus temperature. So you just apply that value linearly between the solidification range. One other way to get those values is to calculate them. And so techniques like CALPHAD, which I'll explain in more detail in a few slides here, can calculate these kinds of material thermophysical properties as a function of temperature and chemistry. And so then you can use that. And you notice if you use the CALPHAD, that's what they've done in the paper here, versus the handbook, you get a completely different peak temperature, completely different cooling rate, completely different time to solidification, which has implications on melt pool shape, etc. And so it's the data that you use or put into your finite element simulation is critical, and that's the point I want to make with this slide. And chemistry can also have an effect. So that previous slide was for a specific heat of 316L. And you may not have the same chemistry as what you're looking up in the handbook. The handbook might not even report what chemistry they've measured the data for. It might just say nominal chemistry. And as we all know, chemistries have spec ranges. And so here we have a Ti 6242, it's a titanium alloy, anomaly 6 aluminum, 2 tin, 4 zirconium, 2 moly, and some trace elements. And here's the spec range over here. And in titanium alloys, one important temperature to know, let's say we do a build on this titanium alloy and we want to heat treat the whole thing. We may want to heat treat above or below the beta transist temperature. And the beta transist temperature is a temperature where the titanium alloy has a allotropic or solid to solid crystal structure transformation. And so we go from beta or BCC to alpha or HCP crystal structure. And this is really useful. Like steels, we can form lots of different microstructures if we have such a transformation like martensite, or in titanium, you can have basket weave or colony alpha, etc. And we can get a lot of different properties. And so it's important to know whether we heat treat above or below this temperature. And with a tool like CALPHAD tools like Thermo-Calc, we can calculate the beta transist temperature as a function of chemistry. And you can see that even within this spec range, it varies. It can vary quite a lot, right? So the nominal may be around 900 or 90 or 1000 C, but for your specific chemistry, it may be plus or minus 20 degrees. Okay, and so at the end of the day, what we are going to be talking about here is, I'm going to focus on additive and the finite element simulations that we can do for additive, but all of these kinds of things are models in this chain here. So we want to go from chemistry and process to talking about microstructure, to using those microstructures to generate some properties, and then go from properties to part performance through some kind of finite element model. And this is what we're going to be talking about here. And so hopefully those two previous examples help illustrate that your process and your chemistries are going to change, and how do we handle that is what we want to illustrate here. Okay, so I hope you learn a few things in this talk today. So try to illustrate there in the last few slides the material data challenge that we all face. Hopefully that's something that resonates with you. And if as a takeaway from the talk I'm going to give today, I hope you can learn a few things. I'm going to talk a little bit about the CALPHAD method and how it works. So if you're not familiar with that, hopefully you can learn something there. I'm also going to talk about the Scheil equation, or the Scheil-Gulliver equation, which is really important for solidification. So if you're not familiar with that, I'll kind of go over the graphical derivation of that, and hopefully that'll be useful to you. And then I'll shift gears after we kind of cover those basics, and I'll talk about the finite element model that we've coupled inside our software and how it works. And we'll go through a case study with alloy 718 that we pulled from the NIST AM-Bench data. And we'll talk about some of the modifications that we've made in our software to handle fluid flow and keyholing phenomenon, and then culminating with predicting process maps, which is ultimately kind of the end goal of simulating these kinds of laser powder bed additive manufacturing processes. We want to be able to simulate the melt pool dimensions and then predict a process map where we can say, hey, here's a good place where we should do our processing. And so CALPHAD is a phase-based approach to modeling the material behavior, as a kind of general way to put it. And at its core, we are solving for the Gibbs free energy. So this is largely a physics-based kind of approach, and that can help it be, makes it very predictive in nature. So we're not just doing some regression fits and trying to say these are the properties of the material. We really look at the Gibbs free energy and we assess the Gibbs free energy change as a function of chemistry and temperature for many phases in a system, and that allows us to learn a lot about the material behavior as a function of chemistry and temperature. And I'll talk more about how that works in a few slides. And over the last, CALPHAD's been around since the 70s, I think, and the software was first developed in the 80s. But over the last, maybe 30 years, this technique's been extended into more and more properties, like diffusion and precipitation, and even more recently, in the last 5 to 10 years, things like resistivity, that covers electrical and thermal, things like molar volumes, densities, elastic properties, and also calculating other kind of phase-based things like martensite, bainite reactions, and things like that. And so at the core, as I mentioned, we're modeling the Gibbs free energy. And so why do we do Gibbs free energy here? Well, that's because it allows us to construct the phase diagram. And apologies, it was supposed to start when I clicked on the slide, but it didn't. And so if you recall, maybe you took if you're from a material science background, or even if you have a mechanical engineering background, you may have taken a course on material thermodynamics. And if we want to make the phase diagram, we need the Gibbs energy curves. And if we can draw a common tangent between the Gibbs energy curves, we can find the phase boundaries of the phase diagram. And so if we can model how the Gibbs energy changes, then we can understand the phase diagram for any system. And this is all very easy to see in a binary system, right? Okay, this is basic binary diagram. That's fine. And you can look up a lot of binary diagrams in the handbooks. But what about systems with more than 3 elements? Well, it turns out that this whole business of assessing the Gibbs energy changes for binary and ternary systems ends up being a giant interpolation problem, and I'll explain what I mean by that. So if we want to calculate for a 10 element system, let's say we've got 10 element, 304L composition, and we want to calculate the phase balance in there, you might think, well, if I only have the data for the binaries and the ternaries, how is that not just extrapolating to 10 elements from a bunch of binaries? Well, if you take this ternary over here, we've got this ternary diagram. It's in 3D space. And you see that the ternary is actually bounded by the binaries. So if I kind of only told you information about the binaries, I give you the AB, the AC, and the CB binary diagrams. And I say, hey, tell me what happens when you mix all these 3 elements together. Well, actually, you're interpolating between those 3 diagrams. Okay, now take that to a 4 element system. You can't probably imagine 4D space in your head, at least I can't. But that 4D system is bounded by all the ternaries that make up that 4D system, and those ternaries are bounded by the binaries that make up each of those ternaries. And you can just keep going to higher order systems, 5 element systems bounded by the quaternaries, and subsequent binaries, etc. And that means that it's basically just a giant interpolation problem. And luckily for us, the interaction parameters get weaker and weaker at higher orders. So it's actually just enough to consider only the binary and ternary databases, or binary and ternary systems. And so a thermodynamic or CALPHAD database is really just a collection of assessments on how does the Gibbs energy change for a bunch of binary and ternary systems. And that works well, and the databases have been developed over many years and now contain many elements and many systems. Okay, so hopefully that gives you a background on how CALPHAD works, kind of in a nutshell there. It's very abbreviated. There are some nice books and papers you can find if you want to learn more. But I'll shift gears here and we'll talk about the overview of the AM module and kind of the motivation behind it, because it's kind of a new space for us as a software company. And we started introducing thermophysical properties in our databases around 2020, and we've added a lot of properties, things like thermal conductivity, surface tension, viscosity, electrical resistivity, etc. All now to be able to be calculated as a function of chemistry and temperature. And traditionally, CALPHAD has always been able to do things like heat capacity and latent heat, because that's directly from the Gibbs energy. And we started to get more and more requests from users. Hey, if you can predict all these properties, why can't we just export them and in finite element codes? And yeah, sure, you can. The problem was a lot of finite element codes couldn't kind of handle the complex nature of the specific heats and the thermal conductivities varying. A lot of finite element codes are intended to take like constant values for a lot of these properties. And so users were having a hard time getting the codes to converge when they put in these more complicated properties, and not treating things in a simplified manner. So this is kind of was a unique possibility for us to try to address this issue. We decided to go with additive, since it's kind of a newer thing and a hot topic. And so we've developed this code here, and we didn't try to rewrite our own finite element code. We're actually using Moose, which is an open source finite element code out of Idaho National Lab that we're using as the solver. And so what we do is we calculate the thermophysical properties, like all the specific heat, latent heat, thermal conductivities, etc., for the alloy that you give the chemistry for, all as a function of temperature. We take into account solidification, which I'm going to talk about in a minute. And then on top of that, we can do then steady state simulations, which are quite quick, just to determine like the melt pool shapes for a given set of laser parameters. So you put in all your laser parameters like the wavelength and the power and travel speed, etc. Or we can do transient simulation like the one that you're seeing right now off to the right, where we can have different scan strategies and add layers and look at the heat distribution and the melt pool shapes as you go and as you build up. Additionally, we can calculate things like printability maps, which I mentioned earlier, the GNR curves, which is the thermal gradient and solidification rate. That's really useful for predicting like columnar to equiax transition, whether or not you're going to have equiax grains or columnar grains. And I'll cover that as well later. And then you can also take the cooling curves. If we kind of put a probe or a thermocouple in our finite element simulation somewhere, we can monitor that temperature and then take that time temperature history out and put it into another one of our codes like precipitation module or diffusion module and see if any precipitation or diffusion is happening to change the microstructure. And so really what this is this is making a unified treatment of both the process parameters and the alloy dependent thermophysical properties. I think this in one sentence is a kind of nice way to say what is going on here in this AM simulation. And then throughout the last couple of years since we developed this, we've added a lot of different things. I don't have time to cover how each one of these things works in this talk, but we have now different heat sources like conical or Gaussian, and we're working on making some new ones I'll talk about later. We simulate fluid flow, which is important for Marangoni effect. Maybe you have heard of Marangoni effect or maybe not, but that's a surface tension effect where you can actually have, depending on the chemistry, especially in stainless steels, when you have like sulfur or silicon, you can get the surface tension as a function of temperature can flip from like a positive to a negative like trend. As you increase temperature, the surface tension either goes down or up or stays flat. And that can cause fluid flow to change directions in the melt pool. And that can totally change the penetration depth or the width of the melt pool because of that effect. And that's very critical to capture for certain chemistries. We can also model the keyhole, which I'll talk about later. And then we have ways to generate the printability map or do batch calculations where you can say, I want to calculate over a large range of powers and speeds and etc. Okay, so I've talked a lot about the material data. We calculate it, we need to get it. Okay, but how do we get it? And how do we make it the most accurate it can be for the given situation that we're dealing with, right? CALPHAD is historically an equilibrium calculation. So we're talking about thermodynamic equilibrium when we calculate all these properties. Well, we all know that additive manufacturing happens very quickly in terms of cooling rate and speeds and things like that, and that's very much not equilibrium, right? That's highly non-equilibrium. And so how do we account for that? And how do we account for the solidification effect on the material behavior and the material properties through thermodynamics? And that is largely done through the Scheil-Gulliver equation, which I will cover here in a second. And then post-solidification, we also have quite rapid cooling. How do we deal with that? We use something called the freeze-in equilibrium. So we actually kind of prevent the phase fractions from changing, but still calculate all the other thermodynamic properties as the material cools down. So that allows for a more accurate description of what's going on. Okay. So I'm gonna switch gears here and kind of give maybe a short lecture on the Scheil-Gulliver equation if you haven't heard of it. And if you have already, hopefully this will be a good review for you. on what the Scheil equation is and how it works. So let's consider a copper 2.5 weight percent alloy. So we've got this alloy here, and I give you the phase diagram, so you can plot the alloy here. It's this red dashed line. And I ask you, what's the solidification temperature range of this alloy? And you might look at the diagram and go, oh, well, the liquidus temperature is about 650 and the solidus temperature is about 600. Now you go cast this alloy into a, cast it or weld it. And also you might say, oh, it's going to be single phase. This is FCC, this region here, this triangle shaped region of the phase diagram. You might say, oh, well, once it's done solidifying, it's going to be single phase, fully FCC. And then once we get to 450, we start to precipitate theta. Theta is over here into this two-phase region here. If you were to cast it or weld it, you would be wrong. You would see in the microstructure that you have eutectic theta upon solidification. And if you were to measure the solidification temperature range through like DTA or something, you would not see a solidus temperature of 600 C. You would probably see a solidus temperature of 550 C. So why is that? So Scheil and Gulliver, which the Gulliver paper is from like 1930s, I think, or I might have it backward. One of them is from 1915 or something like that, and the other one's from the 30s. Made these assumptions. He said, okay, well, we can make phase diagrams, and then when we solidify things, we can make a couple of assumptions. We can assume that diffusion in the liquid is infinitely fast. That's pretty reasonable because diffusion in liquid is much, much faster than solid. And that we cool quickly enough, 10 C per second, 20 C per second, that diffusion in the solid is negligible, that we don't have any diffusion in the solid. So we can trace out how this is going to proceed on the phase diagram if we make those assumptions, okay? So I'll try to go through this kind of quickly in the interest of time, but hopefully you can follow along here. So we've got our alloy, we're cooling down, and we hit the liquidus temperature. Now let's give a little bit of undercooling. So I've kind of undercooled this. I'm going to exaggerate the undercooling on the diagram. So I've undercooled quite a lot here, but let's say we've undercooled a little bit. And now we're in this two-phase region. So the first solid to form will have the chemistry dictated by this point on the phase diagram, right? The first bit of solid that forms this chemistry, and the remaining liquid, let's say we've solidified 10% of the system, the remaining 90% of the system is liquid, and that liquid has this chemistry, right? Because whenever we're in a two-phase region, we use the lever rule to determine the chemistry of the two phases, and we can determine the phase fractions by dividing the lengths of these lines between these 3 points. The ratios of the lengths of the lines to the total length of the line gives you the phase fractions. Now, the solid, we said we were going to say no diffusion. So that solid is fixed. We've formed a little bit of solid, and it has, this chemistry as dictated by this point. So let's say, very small amount of copper, 0.2% copper or something. Okay, the remaining liquid now has this chemistry. So all of the liquid in the system has this chemistry. Let's cool that liquid down a little bit. So we cool this liquid down a little bit. Again, I'm exaggerating here. And the next bit of solid that forms has this chemistry, and the remaining liquid has this chemistry. Okay, so the amount of solid, we've formed some more solid. We'll define a variable, fraction of solid, fraction solidified on the x-axis, and I'll plot chemistry. So this is like weight percent copper on the y-axis. So the amount of copper in the solid is going up, right? Because we've moved from left to right on the x-axis here, and we're solidifying more and more material as we go. Now we solidify this bit of liquid, or the remaining liquid, and it forms some more solid with this chemistry, and you can kind of see where this is going, I hope, by now. And so the remaining liquid gets more and more enriched as we solidify, and continues to enrich until we reach this point, at which point the last bit of liquid to solidify will solidify at the eutectic point. So we will just jump straight, and I'm trying to draw with the mouse, so I apologize for that, until we reach fraction solid 1. So we've fully solidified at the eutectic point. And so what have I kind of drawn here? I've actually drawn the chemistry across the dendrite. We've kind of if we have a dendrite solidifying, the core of the dendrite is the start of solidification, and the boundary between two dendrites is the end of solidification. And we can expect some eutectic at the end of solidification in between the dendrites in interdendritic regions. And if you go make a copper 2.5 weight percent alloy, you will see this in the microstructure. Okay, so the Scheil derivation, I'm not an equations guy. You can do when you draw this picture, and you can make some, small d f of s and some small d chemistry of the liquid, and set the areas equal to each other with some fancy mass balance, and rearrange the variables and get the Scheil-Gulliver equation. Okay, I promise that you can do it with this picture and these areas equal to each other, but I won't do it. And so this is the Scheil equation, or the Scheil-Gulliver equation as we know it. And we can do this in a multi-component system. This equation is kind of for a binary. It's not as easy to solve this equation numerically in a multi-component system. So actually what the software does is this process just in a multi-component system, just lowers the temperature by 1 degree, find the chemistry of the solid, find the chemistry of the liquid, save that, get the new chemistry of the liquid, etc. So this kind of graphical way we did it is the way that the software is solving in the background in a multi-component system. And so this actually gives us a wealth of information related to the solidification and very much the non-equilibrium solidification behavior, how the alloy will actually solidify in real life under those assumptions, right? No diffusion in the solid and infinite diffusion in the liquid. And those assumptions don't always hold up, right? If we cooled very slowly, we might have some diffusion in the solid, but there are some equations and ways that you can handle that. And if we solidify very rapidly, that might also change things, right? And that actually is called solute trapping, we'll talk about. But largely the Scheil describes the chemistry across the dendrites, so from dendrite core to dendrite boundary here, and we can plot a lot of different things. The chemistry across the dendrite, the non-equilibrium solidification range, what phases form on solidification. This is for 718 here. We have lavase phase forming. We have a niobium carbide forming, maybe some sigma and delta phase potentially at the very, very, very end of solidification. And here's what you might measure in the EDS. If you went to the EDS and you measured across the dendrites, you might measure chemistry profiles that look like this. But we can also get all the other thermodynamic variables like the latent heat and the specific heat and the density and thermal conductivity and all of that good stuff. Okay, but this is a talk about additive manufacturing, and especially in laser powder bed, we typically raster or move the laser very, very quickly, and that causes very fast cooling rates and very fast solidification rates, and the normal Scheil does not hold up. So I write here, what about solute trapping? So solute trapping is a phenomenon that happens when solidification happens very rapidly. It is not related to cooling rate, or cooling rate does not dictate whether solute trapping happens or not. I should say that cooling rate is actually a kind of a product of the thermal gradient and the solidification rate. You can actually dimensional analysis the units of thermal gradient and solidification rate cancel out to give the cooling rate. So cooling rate doesn't quite tell the whole story, but solute trapping is a phenomenon that happens when the solidification velocity is very fast, so fast that the atoms don't have time to rearrange themselves across the interface. And so how that manifests is, if you go back to here and you think about this little process we were doing, we were putting a point in a two-phase region and using the lever rule to determine the chemistries of the two phase boundaries, right? The chemistry of the solid and the chemistry of the liquid. And doing that process assumes that the interface is in equilibrium, that we are in equilibrium in the two-phase region. And when you move very, very quickly, solidification-wise, the interface is not in equilibrium. And so that is the part of the Scheil that needs to be modified, okay? And again, I'm not an equations guy. I won't try to go through the derivation, but graphically, if we plot as a function of distance, here it's distance is z, sometimes distance is z, sometimes distance is x. I I guess it's not X because we have X for chemistry here, but anyway, a solid liquid interface will be described by the tie line, right? So that's what we were doing on the phase diagram. So if we have our normal phase diagram, ignore all the stuff in the middle right now. We have our two-phase region here in between the red and the orange. We have the chemistry of the solid and the chemistry of the liquid. Those points will be here in kind of distance space. This is like a snapshot of the solidification happening. Ahead of the solid liquid interface, you might have a gradient in the liquid of chemistry, right? To get back to your nominal composition. And then your solid will be solidifying at some depleted chemistry of solute. And Gibbs energy wise, remember I said we can make the phase diagram from Gibbs energy curves by drawing the common tangent, which would be this line, right? That gives us the red and the orange dots. That's how we find those if we have the Gibbs curves. When we have solute trapping, you can just think of it as these solid and liquid lines get pushed in towards something called the T0 temperature. So if we were to solidify infinitely fast, move that laser at 1,000 meters per second, the liquid would just turn into a solid. There would be no segregation of elements. We would just instantly solidify, right? And that actually would happen at the T0 point, which is this point where the Gibbs energy curves cross each other, where they're equal. And that T0 line, it can be drawn on the phase diagram, typically bisects the phase field like is shown here. Of course, it's not an on or off phenomenon, it's a transitionary phenomenon. And so at certain speeds, like maybe 1 meter per second or 2 meters per second, you'll have some kind of compression of the solid and liquid boundaries. And so I've drawn those here by blue and these two blue dots, the dark blue and the light blue dots here. So basically we just make a new phase diagram for a particular velocity. So for a particular solidification rate, we can make a kind of new phase diagram. Then we can apply the Scheil to that phase diagram. Okay, so that's kind of the basics of what you need to know on how we can handle the rapid solidification that happens in these processes, and how we can take the thermodynamics that we've described at equilibrium and transform those thermodynamics to be able to account for the rapid solidification and hopefully accurately describe the rapid solidification. And it works pretty well. But I should say, you don't always have solute trapping. One thing that's missed by many, I think, is that the solidification velocity is not the travel speed. Okay, so you might, I'm a welding engineer, so I'm going to say travel speed and not raster speed, but the laser is moving, the melt pool is moving, right, in the steady state at the velocity that we're rastering the laser. So let's say we're rastering the laser at 1 meter per second. Okay, so that's our V. V equals 1 meter per second. The dendrites don't grow in that direction. They grow kind of like parallel to the heat flow, and the heat flow will dictate the weld pool shape, right? So the dendrites are kind of, if we look at the side view, I think the side view is easiest to imagine. The dendrites are going to grow this way, right? And so this angle, the speed at which the dendrites grow is actually the cosine of the angle times the velocity. So the faster you go, typically the longer the weld pool gets, and so the steeper this angle gets, which means the speed of the solidification is not that high, right? If this angle is 60, then the actual solidification speed is half of the velocity, right? And if it's 45 degrees, then the solidification speed will be 0.7 whatever it is for cosine of 45, right? So just keep that in mind. We might not always have solute trapping, even if we are solidifying or rastering the laser quite quickly, because the solidification velocity is not always the speed of the melt pool. Okay, and that actually is the case for this NIST AM-Bench case study that we're about to go through. Okay, so that concludes some of the kind of lecture-y type stuff that I wanted to cover today. And now we'll shift gears and look at the real data and see how the simulation stacks up. So if you're not familiar with the NIST AM-Bench series. This is a series they do every year, maybe it's every couple of years. They do like a competition. NIST has these very well instrumented builds that they've made for different materials. The 718 was one of the first ones they did, but now they've expanded that into other materials. So they instrument the heck out of this AM build. And in this case, this one is like single tracks on plate, not with powder, but they've done other powders and things like that too. And they do these kind of challenges you can participate in where you try to model some of the stuff that they've done and see how it stacks up. I think it's pretty good, and the data sets are really comprehensive. They're all free. You can download them on the NIST website. So we've got this nice set of data here where they've measured the melt pool dimensions for a bunch of different changing parameters, right? So we change the spot size, the scan speed, and the laser power, and then measure the melt pool shapes, okay? And since we're going to be simulating the melt pool shapes, this makes for a nice comparison data set to help validate our model. Okay, so first we have to calculate the material properties. So we actually take the chemistry that NIST provide, right? They use a heat of 718, right? I think that's important to capture here. I'm not really talking about that much other than the very beginning of the talk, but every heat of 718 is going to be slightly different chemistry, and that may or may not have a large effect on the thermophysical properties like thermal conductivity, latent heat, etc. Okay, so we calculate all these properties and we use that modified Scheil that I talked about, where we can account for solute trapping, we can account for the kind of freezing in once the material is solidified. I didn't talk about this much, but once the material is solidified, we have that kind of dendrite with chemistry variation across it. And each slice of that dendrite has a different chemistry. And so each slice of that dendrite kind of has different thermophysical properties. And so we have a way to average those together and create like an aggregate thermophysical property data set that is basically of the dendrite. So we kind of have like the dendrite's thermophysical properties from solidification to room temperature. Okay, and I think that's also key. That is key to making the simulation work well and be predictive in nature, because that's really what you have if you do on 718, an additive build and you go look at it right after you build it, you're going to see dendrites everywhere, right? Okay, so the first time we did this data set, we didn't simulate anything related to the keyhole. So keyholing is a phenomenon that happens in laser welds or any kind of high power density heat source thing like E-beam or even arc welding to some extent. And that is a phenomenon where the liquid kind of gets depressed, right? And you have this physical hole as the heat source moves. And initially we didn't have any way to simulate that. So the way to capture the effects is to use the so-called Goldak or double ellipsoid heat source. So if you just apply a Gaussian heat source, which the laser is just a Gaussian heat source, right? Or depending on your beam shape, I guess, but it's just a Gaussian heat source. And if you wanted to try to simulate a keyhole, or if a keyhole actually happens, you would not capture that accurately. And so Goldak in their paper came up with this double ellipsoid heat source. And so the heat source is volumetric. So heat is being applied like subsurface, which helps account for the keyhole. The problem with that is you have to calibrate it. So you need a data set of real data, of real welds or real additive builds, where you measure the melt pool geometry, and then you calibrate this Goldak heat source, basically each color of these lines. You define this double ellipsoid, what it looks like, to be able to make a prediction. And that's fine, and we can do it and get a pretty reasonable calibration as shown here, but that's not very predictive in nature, and that's kind of not our game, right? We want to be as predictive as possible without calibration. So that led us to development of a keyhole model. And so there's a nice paper by Kaplan out there. Again, too many equations for me, but I think all you need to know is that there's an analytical keyhole model that if we know something about the absorptivity, so we actually also have a model we've developed to calculate the absorptivity of the laser, because not all the laser power is absorbed, right? And then there are some reflections we're modeling in here where, there's the laser, what doesn't get absorbed is bounced back out, right? And then absorbed on the other side, and then bounced and absorbed on the front side, whatever's left until, it goes to zero. We can calculate the keyhole shape analytically. So we've implemented this analytical model. I'm not going to go into the detail. And we've also implemented the calculation of the absorptivity as a function of chemistry, and as a function of temperature as well, and as a function of angle, because you need all that because the angles will change in here to be able to calculate the shape of the keyhole. And then that allows us to get rid of using the double ellipsoid heat source. You can still choose it in the software, but you can also do it like this. Okay, so now we reran all this data, right? Okay, so we have the same data set, and now we're just applying a Gaussian, which is basically the size that NIST reported. They've measured the size of the laser beam, and we just put that in, and we calculate the absorptivity, and we turn on the keyhole model, and we get this nice fit, right, with no calibration. Pretty good fit, like within 10 or 15 microns for the most part on width and depth. A little bit better on width than depth. Depth is probably a little more, like 15 microns RMS error, but pretty good prediction of the keyhole as a function of process parameters. And if you recall, there were some varied process parameters on the previous slide. So these pictures here come from this particular case where we have a high power, 325 watts and 960 millimeters per second. And that's great. And we also have these vectors kind of show the fluid flow, because we also have the fluid flow model turned on. So, but what I want to show from here is we can also now generate maps of G and R. So we additionally have a columnar to equiax transition model. So the lines on here are actually calculated for 718. So every alloy will have a slightly different CET transition point. So this purple line is the planar growth region. The blue line is the columnar to mixed transition region, and then the red and the green are kind of when you get more into equiax. So these lines basically are just equiax fractions, right? So columnar to equiax transition models kind of predict, mostly columnar or mostly equiax or mixed. And you can see that many of the points, and these points that are plotted here are from the simulation, and they come from the melt pool boundary, right? So even though we have the scan speed at 960, 960 would be like probably right here. 960 is almost a meter per second. So, 10 to the 0 is 1. So that would be here. And when you see we have no solidification points on this melt pool boundary are solidifying at the travel speed, right? They're all lower than that because of the angle that I talked about. And so the max speed, I think, is somewhere around, I don't know, maybe 500 millimeters per second. And the prediction here is that most of the grains should be columnar. We might have a little bit in the mixed region, but that's still below equiax fraction 0.49. So I would say it's pretty much mostly columnar. And if you look at the microstructures, which actually were recently published by some researchers at NIST, it looks mostly columnar. It's kind of hard to see, but the melt pool boundary is here. You can kind of see the melt pool shape, and it's mostly columnar. So that checks out. Okay, so now that we've got the simulation and we've validated it, now we can make a process map. And the process maps are typically made by, if you want to make one experimentally, you can do what these researchers did here and, run, let's see, 6 by 6, run 36 different experiments with different scan speeds and powers, and take a micrograph of each one and see if you have porosity or not, right? Another way to make them is if you can predict the melt pool shape. There are some kind of simple relationships in the literature that have been discussed where you can say, I'm going to have lack of fusion if the depth of my melt pool is not bigger than the powder layer thickness, right? Or I might have lack of fusion in the inner hatch spacing if the depth of my, halfway point is not deeper than the powder layer thickness, right? So the depth of the hatch halfway divided by T, melt pool spacing. If these are less than 1, then I might have lack of fusion. And there are some criteria for balling, and there are some criteria for keyhole porosity, depending on the the ratio of the width and the depth of the keyhole. And if you can calculate the melt pool shape and you can apply these ratios, then you can kind of draw some boundaries where I might have keyholing up here, and I might have lack of fusion down here, and I might have, no defects here, or conduction mode if you're going for conduction mode. And so we did that for the 718. Actually, keyholing is in most of these 718 builds. So, but they still don't have porosity. So they didn't have keyhole porosity. So the keyholing here I've set to 0.3, which is kind of like if the depth of the keyhole is more than three times bigger than the width, then you might expect keyhole porosity. And so we have this relatively large process window predicted here, and the NIST data actually all falls within this red triangle. So I've calculated much wider parameter space than was done in the NIST case study here. But the NIST case study, I should just note, there were no defects in any of the parameter sets that are shown here. So, okay. So yeah, I think I want to leave a little bit of time for questions. So I'll just summarize quickly here, and then I'll briefly talk about some of the upcoming features for the AM module, and then hopefully be able to leave like 10 minutes or so for questions. So to summarize, if you take anything away from this presentation, please remember, or please take away, that material properties are chemistry and temperature dependent, and even process history dependent, right? So there can be some microstructure effects that I didn't really talk about, but the process history can also play a role. And to be, as predictive as possible, a finite element model needs to capture not only the relevant physics, but use kind of the correct or accurate chemistry-specific material properties. We hope that we're doing that here, and we hope that provides some value to the community at large. As far as upcoming features go, and hopefully also you learned how the shile works in addition to all that stuff. And some upcoming features in the AM module, we're going to have some different kind of beam shapes available. Right now we just have Gaussian beam, but we know that there are many machines out there that are using different beam shape profiles like top hat or ring core or donut. And I think there's like a notation for this, like TEM00, TEM01. If you don't know what that means, don't worry about it. But there's like some standards for beam shapes, and we're going to be implementing those in the software. We're going to be allowing for a little bit more complex scan patterns. Right now, we just have very simple geometries with very simple scan patterns. We're going to be allowing for a little bit more complex ones, and also the ability to add like different delays for like, time where the laser has to wait for the next layer. And I think we already have that, but there's like lift time and stuff like that are going to be added, like acceleration, deceleration of the laser, pulse beams, etc. And we get this request all the time. Can you shoehorn this model for powder bed fusion, for DED and WAM? Can you shoehorn this powder bed fusion model for DED and WAM? And the answer is kind of no at the moment. If you think about it, DED and WAM are adding material, right? And so it's a little bit more complex in the finite element space, because we have to add the volume elements and we have to turn on the mesh like elements as we go, as you are adding material, right? Instead of just turning the whole layer on and then rastering the heat source, and then turn a whole nother layer on and raster the heat source. So that adds a lot of complexity, it adds a lot of calculation expense. And so we're working on that. Here's a example kind of preview of what we've done so far. But to get to this point, we have to make some other assumptions that, related to the heat source and the melt pool and stuff like that. So that's a challenge, and I think there are many directions we could take that, and different complexity levels of how rigorous or how many assumptions we make, that all have trade-offs. And I think we would love feedback from users or even non-users who think that this is interesting, and something that you see a need for. If you have feedback or want to collaborate on the development of this, please reach out to me, um, or our team, and I think that would be very valuable for the development here, because we know that it's something people want to do, but there are many ways we could do it, and there are trade-offs, so we want to figure that out. We can do it together. So yeah, I think at that point I'll wrap up. I appreciate everyone's attention today, and I'll take any questions you may have.
Thanks, Adam. Great detailed presentation on data, real data, material data, data sets, data. Um, Very good, thank you. We do have one question, but I actually wanted to do a plug for you and for actually A2M2X. So anybody that is on the line that wants to see Adam in person, he is going to be here at Lift in Detroit on April 7th, which is our A2M2X event. We would love to have you. If you haven't registered to attend, it's a full day programming. They are going to be in person. They're actually going to be doing a presentation in our technical sessions. And so you can make sure you send some of your folks to join us on that day at A2M2X. So I did have one question that came in, and you might have addressed this in here, but how can you predict residual stress and distortion with these techniques?
Yeah, thanks. That's a great question. We get that a lot. The answer is not quite yet. I think residual stress and distortion requires not only like elastic property data, which we do calculate. I didn't really talk about it, but we can calculate the elastic modulus of materials as a function of chemistry and temperature, and density as well. So to do residual stress and distortion, you need that, but you also need stuff like the flow stress curves, like kind of like a tensile test that's done at different temperatures to understand the plastic deformation that might occur, and that kind of stuff. And that behavior can be really sensitive to microstructure. And so that makes a unified model really hard to develop. So it kind of needs to be like, we have to have a flow stress model for titanium, and a flow stress model for martensitic steels, and a flow stress model for austenitic stainless steels, etc. So that's more work, but we're actively working on some specific models for a couple key material systems that hopefully will be available relatively soon.
Excellent. You did talk about the upcoming features, which I think is really important. And I know that this presentation and this recording and your presentation will be shared with all the registered attendees after this. There was someone that asked about material testing and modeling. They're going to reach out to you directly. I don't know if there's any comments that you wanted to make on materials testing or modeling, or that could happen kind of post this. But other than that, any comments on that, or would you like to take that offline when they reach out to you directly?
Yeah, I think feel free to reach out to me, whoever asked that question. I think there's a lot maybe to digest there. So
Yeah,
yeah,
that's what I thought.
get some specifics
Excellent.
and we can go into detail. Yep.
All right, I will do that. So with that, I would like to thank you, Adam. Great presentation, very detailed. And we appreciate your membership and contribution here at Lift. So thank you. I would like everybody to mark your calendars for our next Liftoff webinar, which actually is next week with our own Beth Kreiderman-Moss on March 26th, who's going to be talking about the Mentor Protege program, building small business defense industrial-based capacity through mentorships. So mark your calendars. Thank you again, everybody, for joining us. Have an awesome day. Thanks again. Bye-bye.
Yep. Thanks, Christine. Thanks, everybody. Bye.